So far, we have taken a look at the world of atoms, molecules, and reactions. And today, we're going to take this knowledge to a much larger scale. Welcome to the field of chemical technology. Chemical technology is all about designing and optimizing chemical processes. As you can imagine, just because you have managed to synthesize a milligram of a new drug in a laboratory doesn't mean that you can then use this to treat the entire world population. The process first needs to be scaled up. And similarly, it takes a lot of chemical engineering efforts to go from being able to convert a small amount of carbon dioxide to ethylene to being able to do that on a scale that's large enough to impact the amount of greenhouse gases in our atmosphere. In this lecture, we will go over some basic techniques used by process engineers to be able to evaluate and optimize chemical processes in a systematic manner. We'll start from a process description, which gives us information about the process and chemicals involved, but this is usually a very long and complicated text. To get a good overview of the process, we'll first translate this description into a flow diagram. Using conservation laws, such as the law of conservation of mass, we can then calculate the unknown quantities. You will see these icons appearing on the next slides as well, so you can keep track of where in the process we are. Let's look at an example to make these concepts a bit more clear. The process description here describes a gas stream which contains 18 weight % hexane, with the remainder consisting of nitrogen. This stream flows into a condenser, where the temperature is lowered and part of this hexane is liquefied. Two streams leave the condenser: a gas stream containing hexane with a mass fraction of 0.05 and a stream of pure hexane in a liquid form, which leaves the condenser with a mass flow rate of 11.47 kilograms per minute. Now, the first thing we do is convert this entire process description into a flow diagram. We draw the condenser as a rectangle, and the process description told us that a gas stream containing 18 weight % hexane entered this condenser. We use an arrow to represent this gas stream. We know that the stream consists of 18 weight % hexane, so a mass fraction of 0.18. The sum of all fractions should of course be 100%. So this tells us that the mass fraction of nitrogen should equal 1 minus 0.18 is 0.82. We write these two fractions underneath the arrow, as they are the composition of this gas flowing into the condenser. We were not told how many kilograms per minute were flowing into the condenser, so we denote this unknown quantity with M1. The dot on the end tells us that we're dealing with a flow rate, so an amount per unit time. The process description also told us that a gas stream with unknown flow rate, M2, containing hexane with a mass fraction of 0.05 came out of this condenser. And that means, of course, that this stream contains a nitrogen mass fraction of 1 minus 0.05 is 0.95. The second stream exiting the condenser was a liquid flow, pure hexane with a mass flow rate of 11.47 kilograms per minute. And that gives us the flow diagram containing all of the information from the process description. From this flow diagram, it's very easy to see that we have two unknown quantities in this process, M1 and M2. And remember to always write the mass or molar flow rate above the arrow, the composition of the flow underneath the arrow, and we place a dot on top of the M or N to indicate that we're talking about flow rates, so a process that is continuously flowing. So far, we haven't really done anything very complicated. We've only translated the process description into a flow diagram. Next, we have to write down the mass balances, using a law that you probably already know, the law of conservation of mass. In a chemical system, this reads accumulation equals input plus generation minus consumption minus output. In a mass balance, there is no consumption or production, and since we're talking about the stationary process, there's no accumulation either. This means that our balance is simplified to 0 equals input minus output, or input equals output. Going back to our flow diagram, we can write down the mass balances for both hexane and nitrogen. The total amount of hexane entering the system equals 0.18 times M1, and the hexane leaves the system in both the gas stream M2 with a mass fraction of 0.05, as well as in the liquid stream M3, which we know equals 11.47 kilograms per minute. Similarly, for nitrogen, we find 0.82 times M1 equals 0.95 times M2. Now you see we formulated two equations with a total of two unknowns. So this system can be solved for M1 and M2. I challenge you to complete the last step, calculate unknowns, by yourself. Try and calculate the flow rates of these two streams. Most real-world chemical processes are a bit more complicated than the example we just worked through, of course. What you see on this slide is the flow diagram showing how CO2 can be converted to the useful chemical ethylene. You might remember this flow diagram from the introduction of this module. In the exercises, you'll have the opportunity to practice with flow diagrams and balances. Good luck!